In this video, we will continue our discussion of simplified PV system design. Let's now look at the second simplified design strategy. This design strategy is a bit more accurate and detailed than the previous, since it requires some additional details as input other than just the PV module type and the connected loads. The second simplified strategy consists of 4 primary steps. As in any PV system design, the first step involves calculating the load demand. By using the so-called load table, we are able to calculate the total energy requirements of the loads on a daily basis. Note that, unlike the previous design strategy, here we make no distinction between AC and the DC loads in the load table. After calculating the load demand, we multiply the total daily energy requirement of the loads by a sizing factor. By adding a sizing factor into your calculations, you are augmenting the energy requirements of the system by a certain value. It is inserted as a safety feature against overconsumption by the loads and to account for losses such as dirt accumulation on the PV modules. As a first approximation, a sizing factor of 1.1, that is an additional 10%, is usually chosen. The product of the load demand and the sizing factor is called the daily demand of the PV system. Just like with the first simplified strategy, we determine the minimum watt peak requirements of the PV system by dividing the daily demand by the number of equivalent sun hours of that location. The minimum PV system watt peak value corresponds to the total PV module watt peak that must be installed. You may notice the table on the left named user input. In this table, you record the specifications of the PV system components. For example, the information about the selected system voltage, PV module specification, charge controller specification, and the presence of maximum power point tracking logic are recorded here. By providing this information, we can start sizing the PV system. To size the system, we first calculate the total number of required PV modules. This number is determined by dividing the above calculated minimum watt peak value by the nominal power of the PV module. Further, in the input table, we have added the usage of a charge controller with an MPPT option. As you know, the MPPT decouples the load voltage from the PV array voltage so that the PV array can be operated at its maximum power point voltage. Thus, the number of PV modules connected in series is calculated by dividing the maximum voltage of the charge controller by the MPP voltage of the PV module. Suppose if the charge controller does not have an MPPT function, the load voltage will determine the PV output voltage. Finally, since we now know the minimum number of modules required and the number of modules that should be connected in series, the number of modules in parallel can be obtained. The next step is designing the battery configuration of the PV system. For this, we enter the input details of the selected battery in the input table to the left. These inputs include designing a depth of discharge value and a number of reserve days, followed by entering the nominal battery voltage and the nominal battery capacity parameters. Based on these, the battery bank is sized by calculating the minimum required ampere hours. Such minimum capacity is obtained by multiplying the daily demand obtained in the previous step and the number of reserve days divided by the product of system voltage and the depth of discharge. The resulting value divided by the nominal battery capacity gives the total number of batteries required. Now, if you divide the battery voltage with the system voltage, the number of batteries in series is obtained, and from this, the number of batteries in parallel is just the total number of batteries divided by the series value. Finally, the last thing you need to size is the inverter. In this respect, we have to look at the power the inverter can handle. Thus, instead of the daily demand, we take the total power of the loads as input. From this total power, we determine the inverter size by dividing it by its efficiency and the power factor value. Note that here, the power factor includes other system losses like cable losses and other types of losses that are not considered until now. We finish the PV system by choosing an inverter voltage that is compatible with the system voltage. From this figure, you can see the complete overview of the different steps involved in this strategy. To recap, design strategies such as the one you saw today are a quick way to calculate the PV system requirements. By including details of additional components such as charge controller type, inverter type, and the MPPT, this design strategy is a bit closer to reality than the design strategy previously discussed. Nevertheless, both are used as a first step to check the suitability of the design for a particular location. In the next set of videos, we are going to learn how to carry out the detailed design of a PV system.